Hello everyone, and thank you for joining our live event today. Before going any further, I'd like to just go through a couple of housekeeping requirements. Okay, so firstly, if you have any issues at all watching or hearing the webinar, please reload your browser. 99% of the time this fixes any issues that there are. If you do try that and you're still having any problems, just put a note into the chat panel and the organisers will get back to you and try and resolve the issue as soon as possible. We also encourage you to ask questions about the material you see today in the Q&A panel as we go. You can mark questions for admin only. We're hosting a live Q&A at the end of the event and we'll try and answer as many of your questions as possible. Okay, so our presenters today are Nicolas Delamare, who's a field application engineer from Lauterbach. He's responsible for overseeing all customer technical support, training and services. And Matthew Hudson is a field application engineer team lead from Rapid Systems, who's responsible for coordinating custom support and evaluations, as well as developing embedded integration libraries and tooling. So we're in really excellent hands. Moving on to today's agenda, here's what we'll be covering today. Following a brief introduction on the challenges faced in gathering evidence to achieve certification, Nicolas will cover hardware, trace for functional safety and how to find the right trace for your chip, followed by Matt, who will talk about the RVS Zero footprint workflow and provide a live demo of the tools. Please don't forget to add your questions to the chat panel and we'll pick these up in the Q&A session at the end. So, generating verification evidence. We need to generate verification evidence for certification. While our title is Test What You Fly, which implies Tier 178C certification for aviation, there are many other verticals that require certification, with only a few listed here. A common method for software verification is to instrument code with additional code that measures timing for coverage or during testing. This approach raises some challenges. Embedded computers don't have infinite RAM to store code, and instrumenting code for timing or coverage analysis takes up space, possibly leading to needing multiple test runs. Instrumentation requires access to source code, which may not always be available. Instrumenting code for verification can also affect timing behavior. When code is instrumented, extra code could be added that can take longer to execute on the CPU that might affect timing results. We can overcome these challenges by getting our verification data with no code instrumentation by using Lauterbach's Trace32 and RVS Zero tools, which our presenters will cover today. I'll now pass on to our first of today's presenters, Nicolas Delamare from Lauterbach. Nicolas, over to you.
Thank you, Andrea. So welcome everyone. For those who don't know Lauterbach, we are providing debug and trace a solution for all common processor architectures on the market. So it's from small microcontrollers to bigger SoCs, and I will specify some of them later. We do provide solutions for the complete product life cycle, so from pre-silicon phase with emulators to in-the-field testing, by also real targets with real hardware debuggers, or even early software developments with virtual targets using GDB or ARM fast model and that kind of stuff. One nice important thing is that, we do support all those architectures and almost all CPUs on the market. We also cover different and support a lot of OSs and hypervisors on the market, and we also provide dedicated tool qualification support kit, which helps customers setting up and qualifying the tools in their environment. Now, if we continue, I will focus on what is an auto trace. And an auto trace is basically a non-intrusive on-chip block, which is then inside the chip, that captures a real-time and cycle-accurate record of what the processor is executing. So what's important to understand here is that there is no instrumentation, no intrusivity. It means that we don't stop the CPU at all. This is typically why it perfectly match today's webinar, which is test what you can fly, because you are basically able to trace the executable code that will be embedded in your product. So with the given example here, we have a clear example of this trace. Today I will be focusing on what is an auto trace, but mostly what is a program trace flow, which is one type of trace that the chip may or may not provide. So assuming it does, you can see here that this trace can capture what the CPU is executing, and that this trace can be retrieved. So let me just turn this on here normally. This trace can be retrieved here on a trace board, and using our trace tool, you can basically retrieve on an off-chip trace buffer this trace that will provide information about what the CPU has executed over time. On the other hand, the CPU may be able to generate data trace, which could be helpful for control and data coupling, which is also something required with the DO or any kind of other field. So for example, the ISO 20262. And all that trace that, again, come from the chip itself can be stored into our trace tools for later analysis. So some of the other feature I wanted to showcase those. So for those who've never seen Trace32 and specifically here PowerView, so what I like to do usually is to summarize the auto trace with 3 key points. First, it can enhance your debug capabilities. So we have a way to replay the trace step by step. It also allows you to perform statistical analysis and also, of course, code coverage measurement as we are tracing what the CPU is executing over time. So yeah, continuing with this, there is 2 types of interface with the trace, the so-called on-chip trace, which is on the left. And basically, you can see here again that you have an embedded trace buffer here, for example, on ARM. It's basically a buffer inside the chip, which can store some trace data. Usual cons are that trace buffer is usually really small, at least nothing compared to the other side. I will explain it later. And that by default, there is no timestamps. And you will see why it matters after. The nice thing is that it only requires a debugger, so just using a JTAG or SWT connections, you can actually just access this buffer and decode the trace. On the other side, there is this off-chip trace diagram, which basically here shows that we are connecting the trace tool to a trace board. So, for example, on an ARM architecture, it's called a TPIU, and we can retrieve this trace. And the pros are that the buffer is way bigger than what the on-chip trace is providing, and also that by default there will be timestamps provided by the tools. The cons is that obviously you requires that first that you have the hardware tools for that, and also that on your target side you have a dedicated trace connector. Regarding the interface, just so that it's appealing to everyone, so depending on the architectures, you may heard different acronyms. So we talk about, for ARM, the ETM mostly, which is the program trace flow for most Cortex RA and M device. We also have the Nexus trace for poor PCs. For RISC-V, if we only talk about the ratified standards, we call about eTrace and nTrace. They are both capable of providing program trace flow. And you also have this for tri-core with the MCDS. On the other hand, you also have serial tracing, which can have also different declination compared to what architecture you're using. So we talk about HSSTP for ARM, Aurora for PowerPC. RISC-V is not clearly defined yet, and we also talk about PCI Express. There are some particular use cases, but it does not interfere with the used interface. When you have an FPGA, you might require to have a specific design on the target that will basically route the trace signals accordingly, and after that, in the end, the interface could be either parallel or serial, depending on what you want and what you can get. So yeah, that's pretty much how it works. So to give a few ideas about the targets that are supporting trace and has that kind of interface, we could talk about the Jacito platform from TI. So it includes tracing both ARM cores and also DSPs, so C6, C20, or C7s. It could be also Core IQ trace, so on PowerPC, etc., with the T-series. It could be any kind of ARM SoCs, S32G2, G3, etc., etc. Here you have a concrete example based on the ARM architectures. As you can see here, there are different type of cores, and each core will generate trace messages, and in the end, everything is going into some other components, which I won't explain today because it's not the point, but it could then come to the on-chip trace buffer, which can then be read out just using a simple debugger, but it could also go to any kind of trace port, so either a serial one or a parallel one using a trace tool. And here, with this example, we can retrieve the trace coming from each core as long as it has a trace capability, and all that can be then processed and analyzed. Now, you may be wondering, okay, why not? But how can I know if my target supports that kind of stuff? And actually, there are two easy ways to get that information. And the first one would be to go into our website and basically search for your targets. And as you can see here on the screen, we have an example for a PolarFire SoC from Microchip. And you should always have an indication about whether or not this specific target support either on-chip trace or off-chip trace or both. And if any case you might not find the information, you can always contact us. Hope this was clear, and handing it over to Matthew for the live demo.
Have I been on mute? Let me just go back there. Thanks, Nicola. Sorry about that. It turns out I was muted. Great. So I'm going to be showing you a solution where we combine Trace32 and RVS. RVS stands for the Raptor Verification Suite. So first, a bit about Raptor Systems. Raptor Systems was founded in 2004. We work mainly with the aerospace and automotive markets. We have offices here in the UK, that's where I am right now, and also in Barcelona in Spain and Novi, Michigan in the USA. So I'm going to be showing you the zero footprint tools today, which are part of this Raptor Verification Suite. RVS for short, and it's a suite of tools for supporting various DO178 verification activities like code coverage to timing analysis to functional testing. Rapiter also offers product-related services, and we have a Mac 178 offering where we provide a solution for analyzing multi-core interference, which is discussed in AMC 2193. So our focus today is on the zero footprint plugins for the Rapiter Verification Suite. These are the versions of our tools that don't use any instrumentation. They work purely at that object code level. Rapid Time Zero is used for timing analysis, including worst case execution time analysis. Rapid Task Zero for schedule visualization, and Rapid Cover Zero for code coverage up to and including DAL-B decision coverage. The way these zero footprint tools work is you provide them with two inputs. The first is the disassembly of your binary image that you're going to run on target. So this could typically be like an ELF file. We process this binary image to produce effectively a file database of the object code. If there happens to be debug symbols in there, then we can also use these to provide some linkage back to the original source code, but that's not required. You can use these tools even when you don't have the original source code available. That's the first input, the binary image. The second you'll see from my diagram is the branch trace from running that image on target. So a branch trace is simply a record of the CPU control flow, the decisions the CPU made as it executed the code. So anytime there's an instruction that would cause the CPU to branch to a new location in the code, it's logged into the branch trace with a timestamp. Now, obviously, this is a lot of data as CPUs run very fast these days, and you need a way of getting that data off the CPU in a timely manner. So this is something that Lauterbach Trace32 really excels at, and it's a great way of capturing that data. So the zero footprint tools from RVS take these two things, the process disassembly and the branch trace, and we can combine those together to produce verification reports for code coverage or for timing. The benefits of this approach over a traditional instrumentation-based approach are you're testing against the real software when you run on target, right? So you haven't altered it in any way, you haven't added instrumentation, you're truly testing what you're going to fly. There also can be less messing around with, say, the build system, because you don't need to change the build system, it just needs the binary. So you don't need to make modifications to your build environment in order to support this workflow. And you can also get data even when you don't have the source code. So if you've got some third-party libraries around and they're compiled, they're delivered to you as compiled binaries, and you're not able to normally analyze them, with this approach you can, because it's working at that object code level. It also means you can potentially do a single test run for functional testing and then use the branch trace from that to generate your coverage and timing data. So instead of doing 3 test runs, one for functional testing, one for coverage, one for timing, where you instrument it differently each time, you can just do one test run, collect that branch trace, and then use that branch trace to produce that coverage and timing. So potentially saving you lots of time instead of having to repeat your test suite, especially if it's a very long running test suite. In addition to all that, you know that the results you get, especially for the timing, are free from any overhead from the instrumentation. So there's no scoping effect from that because there isn't any instrumentation. It's purely what you're going to be flying. And you also don't need to worry about having enough free memory space, right, for instrumentation, because the binary image isn't going to increase in size. You are really testing what you're flying. So I'll just give you a quick overview of each of the tools before I give you the live demo. So Rapid Time Zero is our zero footprint timing analysis tool. So its main purpose is to enable you to perform worst case execution time analysis and optimization. It helps you provide evidence that your software under the worst conditions will still meet its timing deadlines. And it combines those real on-target measurements from that branch trace with its knowledge of the possible paths through your code from analysing that disassembly to produce worst case paths, which can give you worst case timing values. If you're familiar with our instrumentation-based tools, then in the zero footprint version, all the sort of normal features you'd expect from RappiTime are there. So you can merge timing reports from different sources to support incremental workflows. You can get lots of different views on the data, so you can really drill down into the nitty-gritty and see things, say, even like the block level. You can replay those recorded branch traces and see where the control flow went. And of course, there's exports, so you can use these exports for certification evidence. So I've mentioned this worst case algorithm. So I'm just going to give you an overview so you get a flavor for how it works. You can see here on the slide, I've got some source code on the right, and then so it's got two ifs there, each with a else branch. And on the left-hand side, I've got a control flow representation of that source code. So the numbers in the little square are roughly like how long it's going to take each of those blocks of code to execute. So you can see I've plotted against this a blue line that's showing one possible path you can take through the code. So we're taking both true branches in this first instance. And so if we add up all the times in the little squares to say, oh, this is how long each block takes, then it comes to this figure 110. So we say, oh, maybe this is my first test case. And when I take the time from that test case, it takes 110 cycles to run through this function. Now, maybe I want to run a second test case against this piece of code. And maybe that test case goes through all the false branches this time. So it goes through all those else blocks. And if we add up those times, then it's going to come to this 85. So at this point, you might think, oh, I've tested really well. I've got full decision coverage. This would give you full MCDC. So we've run all our tests, and we saw, oh, after all my test suite, it never exceeded 110 cycles. We're doing really well. But the eagle-eyed among you may have spotted that there is a third, longer possible path through this code. So if we combine the worst bits of both paths that we did, we can get this sort of calculated path. So if we first go through the false branch of the first if and then the true branch of the second if, we can get this bigger value of 140. So this is roughly what RappiTime's worst case algorithm is doing. It takes the worst bits of each path and the worst observed values for every block of code run, and it basically chooses the worst thing that could possibly happen. So it didn't have to have observed this case. It's able to construct it from many observations that we've done across your source code and that knowledge of the control flow. So that's a bit about RappiTime there. So moving on. RappiTask0 is our schedule visualization tool. So it's going to let you quickly see what tasks were running on your system, what was interrupting each other. It helps you understand rare timing events, so good for looking into when you've got like priority inversion going on, and good for analyzing, say, system capacity issues. And finally, RappiCover0 is a tool for structural code coverage analysis up to and including DAL-B decision coverage for DO178C. It provides you a source to object code mapping with this coverage that can help support object code verification objectives for DAL-A projects. All the normal features are available that you would expect from the instrumented version of RappiCover. So in the zero footprint version, you can see what code coverage came from what test. You can merge coverage from multiple tests and builds. You can analyze, this is I guess specific to zero, you can analyze coverage in third-party libraries. And you can also mark code as covered by manual analysis with the justification feature, and that can also be we can also automatically migrate those bits of manual analysis when your code changes. And of course, we have exports for supporting your certification evidence. Great. Okay, so enough slides for now. Oh, there's one more actually. I'm going to move on to the live demo now. So this is what we're going to be running the demo on. It's the TMS 570. And I've got this connected up to the Trace32 from Lauterbach. To allow for easy loading, I'm just going to flash my image to the target using this JTAG port, and we're going to be collecting a branch trace today, so all that program flow data using these two ETM ports that you can see that I've got my Lauterbach connected to. My host machine is able to connect to this Lauterbach debugger over Ethernet, although you can also use USB. It's just one configuration change. Cool. So let me share my screen and we can see the tool in action. Oh, infinite mirrors. Great. So what you're seeing here is the RVS project manager. This is the graphical entry point to all the tools. On the right hand side here, I zoom in, we've got the workflow, and this is what the actions we're going to run in order to produce our verification data. All these workflow actions, even though there's big buttons here, you can also do it on the command line. So always, Rakta, want to keep things we can keep things automatable. So we even include a little command line builder, so I can tick these boxes and then it will write the command line I need to copy and paste into, say, a shell script or into my CI system if I wanted to automate this whole thing. I have my configurations set up in this drop-down. So I've got one for timing that I'm going to show you and one for coverage. I'm going to start with timing. And to prove it's real as well, hey, I've got a little camera feed here of the Lauterbach connected to the TMS 570 here. It's not doing much right now, but there it is live. Okay, cool. So my first step is to run the prepare stage. So what will happen is we will analyze the disassembly of the binary image of my project. So this is something that will eventually be loaded to the TMS 570. We are not going to add instrumentation in any way. It's purely just an analysis of the binary. In my build, I've included debug symbols, so we are able to map back to the original source code. Now that that prepare stage has finished, I can see the structure of my code. If I just pop down to this analysis tab, we can see it's got a view of all my files, folders, and functions. So now that we've built that file database that knows all about the disassembly, we can now run on target. So let's dock this to the side and click run. So I brought up Trace32. So this run stage will flash that image to the target. It's the original image. And we've got it set up so that we, once it's finished loading here, it's going to enable that program flow tracing. So the Lauterbach is collecting that data as it runs. Trace32 collects that data, and then I've got a few tests that run, and each time a test is run, it outputs that branch data to a file, and then RVS is able to process that file, and we can use that to produce our reports. So that's all done. We now have a timing report. So here we're seeing a rapid time 0 report. Up at the top here, we can see the sort of context for my report. I've chosen today just to have one task that I'm analyzing. And so we've got this update display function. So this is a function that's called again and again and again in a loop in order to implement a display. we are going to now see in this report that everything, all the functions in the report will be in the context of this one function. So this is the task function, and then all the other functions we see are in the cool tree of this one. So you understand that. If we had multiple tasks, then we could see those as well. We could drill down into their own rapid time reports. Along the bottom here, we have different tabs, which are going to show me different views on my data. I'm going to switch now to this invocations tab. So this shows the end-to-end timing measurements for each run of my update display function. And so we can see how long at the moment in cycles each one of these took. We can, down here, expand and see, say on this run 12 here, how long each of these calls in the call tree of this task took to execute. And you'll notice that this run number 12 here is highlighted in purple. So this one's a special one because it's the longest observed run of my task here. And it's highlighted in purple because it is the high watermark run. So if I switch now back to the execution time tab, you can see there is a purple bar which corresponds to that. So the high watermark is important because it represents the test case that stressed the system the most, the one which had the longest observed execution time so far. So if you think back to our slides, that will say test case 1, which ran through that control flow diagram. But you see we're displaying some other metrics here, so I've zoomed in to see some overall execution time metrics. So yellow here for each function is showing the minimum observed execution time. Green is showing the average, so the mean. Purple is how long this function took to run on the longest run of the task. So that is, if we see values for the high watermark, they're always in the context of this 12th run here, the longest run of my task that was observed. We have red, which is the maximum observed execution time for the function across all the runs of the task. So when we see a max value, it's the maximum time observed for that element across all the runs, not just the longest run. And so these first 4 values, these are all sort of observed things. They're things that happened. This 5th value here, this blue one, is different. So this is a calculated value. This is our worst case execution time. So like I mentioned before, we've taken observations of all the time it takes to execute every little block of code. And we know the possible branches that can be taken through the code. And so we're able to combine those together to take the worst possible branch each time and produce this worst case execution time value. So we're going to assume loops iterate the maximum number of times and every block executes the maximum observed amount of time. And so I can get, I'm not just restricted to sticking at this high level, I can drill down now into my function, and I can see now data, the, say, loops here, the loop level or the individual block level. Let me just turn on this so we can now see how long each, say, transition in this code took to execute. We can view the timing characteristics, so we can get an execution time profile of particular bits of code. So let's sort these and choose a good one here. So we can see here a distribution of the execution times for this specific block. This is also available at the function level as well. So it really helps me understand the behavior, and we can get these cumulative profiles, which I really like, because you can select a point on this graph, say, oh, and it will tell you what's the chance that if I took a random sample out of all the samples of this element that would see a execution time greater than 209 cycles, and it's telling me, yep, the chance of that is about 18%, or a probability of 0.18. So we can also view the data displayed on top of the source code as well. So if I click on a source code location or click this source code button, we are now seeing a side-by-side view of the object code and how it maps to the source code on the right, because they were able to use those dwarf debug symbols to map it back. And you'll notice that we've got some pretty colors going on, some highlighting. Let me just take these down. So the first one we're seeing is this green and red. So this is showing what's been executed and what hasn't been executed. So green is executed, red is not executed. If I pop on the high watermark path here, HWM, now this is showing me that best test case we had, test case 12 when we executed the 12th run of this task. It's showing me here where it went with highlights. And if we want some frequency information like, oh, how many times was this thing executed, we can right-click and hover over and get that information. And the final one I'm going to turn on here is this worst case path highlighting. So this is that calculated path where the tools combined all the, the worst possible things that could happen and has highlighted on top of now the code this blue color to show where that worst case path goes. And you'll notice here we have an interesting deviation between the high watermark, my current best test case, and the suggested worst case path from the tool. And so where these deviations occur is very interesting to the RappiTime workflow. It's kind of one of the sort of core things that you'll often be interested in when doing some analysis with RappiTime. So this moves on nicely to showing the contribution time tab. So this tab, let me go back up one level here. So the contribution time tab is now showing how much each function itself, excluding its calls, contributed to a particular metric. So this does take into account the frequency of this item, say the function, on the path in consideration. So we are very interested in when there's a deviation between the high watermark path and the worst case. And this view will let me identify where the biggest deviations are. So when there's a big difference between the high watermark and the worst case, this represents a place where I can potentially improve my timing testing a lot. So it's indicating to me to say this update display and this render rule slots function that maybe I could write a test that would better test and better stress these functions to exhibit more close to the worst case behavior. Because this is my current best test case, and this is what the tool is suggesting might be a path through the code that would be worse. And so what you'll often do in the recommended workflow from RappiTime is you'll use the information we provide, drilling down, and you will write tests to push up this high watermark number to make it higher. Or you can also tell our tool a bit more about like constraints and infeasible paths, and you can push this analysis number down. And basically you'll iterate doing that, writing better tests and improving the analysis until you can get these purple and blue bars to be as close together as possible. But the real key thing here is RappiTime is providing you a way to guide your engineering effort into improving your timing testing. And potentially you can also use this to optimize your worst case behavior because you're able to tease that out using the data. And like on the execution time tab, I can really drill down and I can see now how individual blocks of code themselves are contributing to metrics. So it really gives me kind of a microscope on what's going on in terms of the timing behavior of my tasks. There's lots of other views on this data, so we can for example, see an invocation timeline. So this is giving me, if I zoom in here, I can see here a little icicle graph of the call structure and how long calls took when running. So we've got our update display function, which calls a bunch of other functions, which call other functions, and we can see how long they take, and we get highlighted in purple here ones that are used for the high watermark measurement. So that's the longest observed ones. We can also in other places observe like which runs the maximum came from. Must be another one. So say here, the red is showing where that max run came from. This is also available in the table. So just giving me a nice view on the data. We can see aggregate profiles. So when we want to compare and contrast those important metrics, and we can say make the size of this bar the worst case contribution, and then the color the high watermark contribution. And this can give me an idea of, again, places where I need to spend some effort to improve my timing testing. We also have merge tools. So if you want to, you can, maybe you've got two people working on doing this timing analysis and you want to merge two reports together. We've got a tool that can do this. You can also do it on the command line. And we also can compare reports. So maybe I've got a report that I made earlier here. We can now take the diff of these two reports and see how they are different. And so we're seeing the results from one report minus the other report. And we get these nice graphs, and we can see that how they differ in terms of like what's their execution time and contribution time to particular metrics. So that's RAPI time in a nutshell there. It's a big toolbox of things that you can do. Let's switch now quickly to our coverage tool, and I'll process the branch trace. So you'll notice here I don't need to rerun the executable. I can just reprocess the existing branch trace. So showing that we don't need to keep rerunning the test suite. We could run it once and potentially get this coverage and timing data. So here we're seeing a RAPI cover report. We're on the summary page here, and we've got function entry, exit statement, and decision coverage. Along the bottom, we've got different tabs, which will let us view these metrics. We can see function, statement, decision coverage, and we can expand out this tree and see the coverage achieved on different folders, files, and functions. We go back to, say, our update display here. We can view this data again in the context of the source code. And so like with RAPI time, I can have highlights, but this time we're seeing coverage. So we can see our function coverage, our statement coverage, our decision coverage. We'll also get nice views like tree maps, which is a good hierarchy of my coverage data. So I'm seeing a hierarchy of boxes of folder, file, and function. And the bigger the box, the more coverage elements there are. And so that gives me a nice pictorial way to see my coverage. We can, because you'll remember me mentioning that I ran a few tests. So I ran 4 tests here. And what we can do is we can see which tests produced what coverage with this. So maybe at the moment I'm seeing tests coverage from all 4 of my tests, or maybe I'm just interested in the coverage achieved by test 1. I can turn that off, all the others off, and now my whole report is reflecting just the coverage achieved by test 1. And we can do this the other way around as well. So I can select a particular part of my code, either from my tables or from that source code view. Could even do it from the assembly here, and we can show, oh, tell me which tests cover this bit of code, and RAPI cover is able to show me that. We also have an optimal subset of tests feature that will basically, if you give it a subset of the code, it will calculate the minimum set of tests in terms of cost that will get you the same amount of coverage. And we also have a justifications feature for allowing you to record your manual analysis. So sometimes when you're doing your testing, you'll find some code that you're not able to write a test for, especially with a high-level test. So maybe that's because you have some defensive code. So here I've got an example where I've got a switch block. Got to remove this. I've got a switch block. Let me just delete this here. Where we've already enumerated through all the possible cases, but maybe my coding standard requires me to always have a default case, but I can't actually write a test to cover this. So what we can do in RAPI cover is record our manual analysis with a justification. I'm going to select to create a new justification. Let's dock this interface to the side. And we can give it a title and a description, defensive code. And the report will update now, and in our reports, in our tables, graphs and exports, it's going to show this is covered by manual analysis. And the great thing is this is managed by the tool. So instead of having like a massive Excel spreadsheet with line numbers, it's instead stored by the tool in these managed XML files that you can commit to version control. And because it's able to associate not just with a line number, but by the structure of your source code, we can automatically migrate these when your source code changes based on a tolerance level. And when it exceeds a tolerance threshold, like maybe the function changes, it's able to flag it for human review, but still make a good suggestion on where it thinks this justification can apply. So another time-saving feature. Of course, like with RapidTime, we can compare reports, and we also have a merge tool as well. So I could take, say, two reports. So let's look at A here and B. So I've got two different reports here. We're able to merge their code coverage together using the merge tool. So A, and I'm going to add to it B, use the output location, call that merge, and click this button. And now Rapid Cover 0 merges these two reports together, and I can see the aggregate of the coverage. And by default, we keep track of where the coverage in each of these tests came from. So it keeps the report name here as well. Of course, we have exports. So if I click my export button here, it will export some HTML. We also have CSV, XML, and two different text formats. Exports are also available for timing, and so I can see a nice HTML report here of all my coverage achieved. Great. Oh, infinite mirrors again. I stop my screen share. So back to the slideshow. Where are the slides? Here we go. There we go. There we go. So yeah, in conclusion, we have shown like a combined approach that lets you gather verification data for instrumentation using this branch trace approach, where you can gather verification data without instrumentation using the branch trace, so you can really test what you fly. The Lauterbach hardware supports a huge list of targets, so we'll be able to work with you and with Lauterbach, and we can get a really good solution for your platform. There's a nice smooth integration between Trace32 and RVS, and you can potentially save a lot of time by not having to repeat test runs for different verification metrics, and there's no overhead when you're using this zero approach, so it can even work when you're a bit low on, say, memory space. And we can also use this object to source code coverage to help support the source to object code traceability objectives for DO178 DALE. So thank you for listening. Back to you, Andrea.
Thank you, Matt. Thank you, Nicola, for your presentations and demonstration. Before we move on to the Q&A, I just wanted to mention that both Lauterbach and Rapida Systems will be exhibiting at the Avionics and Testing Innovations Conference, which is taking place on the 2nd and 3rd of June at the Radisson Red Hotel in London at Heathrow. So if you want to come along and speak to the experts there, please do. If you've got the last few minutes, if you want to add any more questions into the Q&A, we'll move on to that. Thank you everyone for your questions. We'll try and get through as many as possible. If we don't manage to answer your question today, we'll certainly try and get them answered via email by one of our experts. So moving on to our first question. It's a question on trace. So this is for you, Nicolas. Do the traces, either on chip or off chip, produce any interference channel effect? I.e., how much does the tracing slow down and memory access across shred fabric?
Yeah, so that's a good question. So first, you have to keep in mind that those trace blocks, besides the architectures, are meant to be as less intrusive and as less interference as possible. But there are cases where you will have interference, and one example is typically the PCI trace or the ETR trace on ARM architecture, where indeed you will have to use AXI access to write the trace to memory, or with the PCI to write on the PCI memory. This will create some interference on the interconnect, for example. But besides that, if I take the more convenient use case, which I showed, which is the off-chip trace, so for example, a parallel one or a serial one, you will not have any interference at all because the trace is designed and has its own trace bus, which is called the ATB on ARM. So yeah, this is what I can answer.
Thanks, Nicolas. Question for you, Matt. Can I identify which coverage results relate to a particular test run?
Oh, yes, yeah. So this is something I just show in the demo. So yes, we can do it both ways round. So you can make a coverage report be in the context of just certain tests. So you can turn on and off the coverage achieved by those. Or you can right-click, say, on a table or on the source code in it. You can say, oh, which tests covered this piece of code. Now, I say tests. These are what we call data sets. So it depends. Well, the way it was working in my demonstration was I had set the target running, and then I had dumped the branch trace to a file. So each of those tests was a data set, which was a file of collected branch data. And so as long as you are making sure that you have like a separate dump per one of those tests, then yes, you can see what tests produced what coverage.
Thanks, Matt. Question for you, Nicolas. How can I know if my target has either on-chip trace or off-chip trace?
Yes, so as mentioned in the slide, there are two easy ways to get that answer. Is either to contact us directly through email, so we can, I don't know if the slides will be sent out, sorry for that question, but anyway, yeah, feel free to contact me. I can send you my email, or you can ask on our website. Basically, you can type the targets you have, and you should have most of the time the right answer, telling you whether or not there are on-chip or off-chip trace capabilities.
Thanks, Nicolas. Another question for third-party libraries, I assume that's lib libraries. As we could not have sources, what do we lose if the different runs have different cycles? For example, different values for loop control var. How max is it calculated?
Okay, so that's talking about a bit about like that worst case algorithm. So for the context of timing reports. So yeah, it's going to go purely off the structure of the object code. So we're always working at that object code level with RAPI times 0, and then it just maps back that view onto the source code. But the control flow graph that RAPI times 0 has in its head is where the branches in the object code go. So you don't lose anything at that level with loops. What you do lose when you don't have the source code is that nice mapping back to the source code, because we are dependent upon the debug symbols. But otherwise, the control flow graph should be the same.
Thanks, Matt. Nicola, why would I use hardware trace and not instrumented trace?
Good question. So the thing is, with the off-chip trace, you have more convenient because you can have larger buffer. Our tools provide also a streaming mode, which allow the user to basically stream the trace to the PC. So the use case is typically functional testing. You can perform large test campaign and trace the whole thing and then import that to RVS tools and get both timing analysis and cut coverage analysis. So it's a huge profit on the time, so this is why I would recommend using the off-chip trace as much as possible. On the other hand, if you can only rely on an on-chip trace, which can sometimes happen, keep in mind that you can still do things. You might have to do several traces and accumulate them over and over and over again in order to reach out the maximum coverage you can do by doing functional testing. But it's also doable. Maybe less convenient, I have to agree, but still doable.
Thanks, Nicolas. Okay, your slide mentioned, I think this might be for Matt, your slide mentioned there's no defined trace mechanism for RISC-V. Is there any proposed standard? Would it make sense to use an existing standard such as an ETM?
Actually, if I can correct that, on the RISC-V side, only the CL trace is not clearly specified. But as of today, for both standards, so N-trace and E-trace, they both rely on a parallel trace, so it works pretty much the same as all the other architectures. So, for example, ARM, it's based on the same standards on the IDE. So just to fix that question. And what was the next part of the question? If you can read it again for me. I think you're muted.
Okay. Says your slides said there is no defined trace mechanism for RISC-V. Is there any proposed standard? Would it make sense to use an existing standard, for example, ETM?
Okay, yeah, so I pretty much answered that question. I believe, feel free to complete that or to ask something again if not. But yeah, as I mentioned, there is already something defined on the parallel side of the trace standards. But indeed, for the CL trace, it's just starting. So it will come along for sure. It will follow, and you should have something really similar to the so-called HSSTP for ARM on those standards in the future.
Thank you, Nicolas. Question for you, Matt. Can I use justifications on zero coverage report as I can with the instrumented version?
Yes. Currently, RapidCover 0, we only support up to decision level coverage, but any justifications for statements, decisions, and functions, yes, you can use them as normal. MCDC, if you're justifying at that level, it would only be for the instrumented version of RapidCover. And
a question on RapidCover is, what's the difference between 3.23 and 3.25?
There's probably quite a lot, so I'd encourage you to look at, I think there'll be a roadmap on our website, and also I can, if you contact us, we can send you release notes. They are also included in the installers, so if you look in the doc folder of the installer of your install, you can see release notes and a change log for lots of detail.
Okay, thank you both very much. We're up onto the hour now, so I think we're just about to wrap things up. If anybody has any other questions, you can always email us at info@rapidsystems.com or info@louterback.com. Thanks to everybody that's attended today's event. We will try and get back to you with answers to emails and questions that we've received this afternoon. Thank you to Nicolas and to Matt for their presentations. I hope everybody enjoys the rest of the day, and we'll end the webinar now. So thank you everybody for joining us this afternoon. Thank you very much.
Thank you.
Thank you.